one at the back.
I tried for a little while.
Give it a whirl. It's a fun curve fitting problem. If you remember that from Math 111, you would make a scatter plot of the data. It's quadratic. There's an AX squared model that fits it beautifully, but that's whatever. It's extra credit. Hopefully everything else was straightforward. Whatever. The very last problem. Hopefully you guys weren't getting one. It was extra credit. Very last problem. But the probability distribution was okay as far as just finding that last little spot that was there, and then figuring the average. And a couple questions came up with there's no standard deviation. There is. There's a population standard deviation, sigma. Remember on the in-class quiz you guys turned in last week? That was one of the things I said I'm going to give you a point for writing it down. You don't use it all that much, but here it is. I mean, when you run one-bar stats, it gives you an average and a standard deviation. When you run sample data, how many standard deviations does it give you? Sample data. 2. It gives you a sample standard deviation and little sigma, which is the population standard deviation. So when you run one-bar stats on that data, it leaves one blank, as you saw, and it gives you sigma, which is the population. But if you didn't get that one, don't worry about it. You'll get them back on Tuesday with a rainy day coupon, and you fix it. Scott?
Is it going to matter whether we put a plus or minus in front of the sigma?
Oh God, no. I don't care about that. Okay. But the fact you're putting a plus or a minus in front of it just means that you realize it can go either way. That makes me happy. Okay. I mean, the numerical quantity is what I was looking for in that one. I mean, by definition, it's positive, but I don't care. Because that means, like I said, you know where it goes. Totally fine with that. Yeah, not a problem at all. So yeah, were the box plots okay? Hopefully that didn't seem tricky. It wasn't supposed to be tricky. It was supposed to just be factual. Did you like the box plot with the Italian cars?
Yeah, I didn't get the Italian bit at all.
I don't know if I asked you a question about the Italian.
Only 1 or 2 Italian cars, and that's.
So the box plot for the Italian cars. Let me throw it back up here again real quick. There's your Italian. Now remember, each one of these samples has 20 cars in it. What does that mean about the Italian cars?
20 cars.
They only have one style, or all 20 styles have the same miles per gallon. They all got about 28 miles per gallon, every single car. That's all that means. It means everything collapses down, Q1, Q3, Q2, everything. So the question where it asks name one country where Q1 equals the min.
There could be 2.
You could use Italy if you wanted to. Okay. Or you could, I'm guessing most of you use Sweden. Yeah. I'm guessing. I think that's it, right? Yeah. But you could have used Italy, because Italy, everything equals the Q1. Yeah, everything does. So. Cool? I wasn't, again, not trying to be tricky. Just trying to be very factual, very straightforward. Hopefully the out of class gives you a little bit more pause, makes you think a little bit more, at least about how you're answering things. That's all. Cool?
I have a question.
Please.
Now, why I chose Italy? Why did you choose Sweden?
I'm saying you could choose either.
Right.
See, there's no whiskers on Sweden.
Oh, because there's no whiskers.
But there are. It's just that the whiskers have collapsed into the box, which means the min value of Sweden is the same as the Q1 value. So what is that? Let's call that 20 just to make it a nice number. That means there were like 6 cars that got 20 miles per gallon. The lowest 25% were all 20, plus the next smallest in the next 25% were also 20. That's all. It just means they've collapsed down. And you see these. You will see these from time to time as you skate through data. When you get some consistent runs of data, that's how they'll show on box plots. That's why I like looking at a whole bunch at once, because you get that idea of range and variance and things like that. I asked you about variance, right? List in order of variance, highest to greatest, or whatever, or highest to least. Good. Good. So that's that. So looking forward, your out of class is due is it Tuesday?
Tuesday.
And then I think I have a project Thursday. And I apologize for that. I do apologize for that. I do. I'm not trying to sing to you. Sing the police to you. Yeah, Tuesday, yeah? Okay. Yes. I think. I try to keep the out of class to do like the next class from the in class. That way, on Tuesday, you'll get this back. And then you can grab the coupons, do any fixes, and then resubmit them on Thursday. And that way the assessment kind of takes, if you will, like a week and a half. Okay. Both parts kind of work together and it's taking a substantial chunk of the term. And then the project is kind of an oddball. It's a lot of Excel. Has anybody taken a look at it yet? Maybe you have, maybe you haven't. A lot of it is, remember the Chuck-a-Luck simulation I ran in class to get those probabilities that we needed for that one problem? Oh, FYI, I put a quiz up for next week. Remember how I said, how do you ask that awesome question in class yesterday about E1 and E2 from that homework? And we ran through E1 and then we started running E2. I was like, you guys just finish it. I realized you probably won't unless I make it worth points. So I did. So I put the quiz up next week, finish E2. So that problem that we started in class yesterday, the second problem that we started at the beginning of class, where we were adjusting the ante on Chuck-a-Luck to make the game fair. We pretty much set the whole thing up in class, and then I said, now just go finish it. So I made that the quiz for next week. Should you choose to do the quiz? You don't have to, of course, but should you choose to finish the quiz, tell me how much the ante should be to make the game fair. I think hopefully I gave you enough hints on that quiz you can see what we're getting at. But anyway, that's Thursday, and so is the project. Now the oddball thing about the project is, all of your out-of-class components are going to have an Excel sheet attached to them. Your first one did, this one does, the next one will. This project does as well. Quite a bit of it is holding down the F9 button. And the project, this is why they're 15 pages long. Jenny was mentioning that before. Like, my God, your projects are 22. They're tomes. Because I'm explaining to you how to use that F9 button and what it does. And making sure that I take plenty of screenshots so that when you're running it, you can kind of make yours match what I'm doing and you don't get lost. You can always ask me if you get stuck or work with each other. I got no problem with that either. But hopefully I kind of head some of that off with good explanation and things like that. So the project's a little bit odd. There's a little bit of mathiness in the beginning, a smidge of mathiness. You're going to analyze your passwords at COCC and the COCC network and whether or not you should feel good about the length of the password they require. You guys, I'm sure, have, well, you're pretty young, some of you. Back in the day when I got my first Hotmail account, all they required was a 4-digit password. 4 digits, that was it. And before that, even in the early 90s, I remember sitting in a, it's something, if I told you the story, you can stop me. Sitting in the van, driving around going to shows, and one of the guys, one of our roadies at the time, had one of those little personal organizers. This is back in the day before cell phones, you know. So everything was digital. It was the bomb, dude. That little flip-up thing with all the phone numbers in it. It was cool. And it was password protected. And he forgot his password. He's like, I can't get to my phone numbers. So cute thinking about this, even saying this out loud. And I'm like, well, dude, how many digits is your password? He's like, I don't know, I don't remember. So I pick up the thing and flip it open and go to the menu, and it says password retrieval. I'm like, oh, let's check this out. And then it tells you that the password is 2 digits long.
Oh.
And I'm like, well, dude, I'm just gonna start trying them until I get it. And I start, you know, just going through 0, 0, 0, 1, 0, 2, 0, 3. And he starts saying, dude, you're never gonna get it. And I hit it back, here you go. And he's like, how did you do that so fast, Magic Man? And I said, well, dude, there were 100 numbers to try. And we're driving like 6 hours to Erie, Pennsylvania to play a show. I think I got the time. And it ended up being 12 or something like that. So I hit it like right at. But that's the idea of the project, is that nobody has 2-digit passwords anymore. Because some idiot with 2 thumbs can crack it in 15 seconds. Right? I mean, and my first Hotmail account had 4 digits. And some idiot with 2 thumbs can probably crack that in about an hour. Max. I don't know how quickly or how accurately they can do it. So now your passwords not only have numbers, they've got letters, they've got characters, they differentiate uppercase and lowercase, you can underscore, right? They tell you not to pick things that are obvious to guess. So you're going to analyze the mathematics of passwords in the first part of the project, which I think is fascinating. And it blows my mind when you think about how long it takes a computer to brute force your password. That's the part I like the most about this project. In that first part of it is, if a computer brute forces, now I just told you I cracked Jay McGettigan, never forget that guy, we stapled him to the loft one day. I cracked his password in like 15 seconds, right, my thumbs. A supercomputer can generate about 1 billion passwords a second and test them all. It's incredible to think about what these and this is now, I mean 10 years from now it'll be even exponentially higher. Computing power is exponential. So to think about that, and then to think about how things like banking industries, schools, anybody that keeps personal information is protecting that using passwords. They keep getting longer, they keep getting more complex. That's because computers keep getting faster and keep getting more and more clever about cracking them. So it's this wonderful like ebb and flow, like predator-prey model of hackers and password generators. So you'll analyze that for the first part of your project. The next part is just how to generate interesting probabilities that might be extraordinarily hard to think about. How many of you guys play poker? Poker? Do you guys play Texas Hold'em?
Yeah.
Okay, so there's a probability that was thrown at me by a number of people. I'm going to paraphrase it, I'm sure I'm going to say it wrong. Drawing a flush. What's like the third card that comes over? You get 2 and then they start turning cards over. The turn, it's one of those. Like what's the probability of sitting dealer's right 3rd place and getting a flush drawn on the river or some random, and poker players always tell me it's 1 in 500, it's 1 in 500. I'm like, how do you know that? And they just, I don't know, somebody told me it's 1 in 500. I'm like, did you question that? And they're like, they look at me like, should I? I mean, these are people that aren't making a lot of money playing poker. So then they start thinking, maybe I should question that, right? So what you're going to do, you're going to simulate sitting a certain number of seats away from the dealer in a Texas Hold'em match. And every time you press F9, you're going to see 1,000 hands of poker played. And you're going to keep track of how many times flushes are drawn in that seating position on that card. This is an impossible problem to do by hand. You cannot do it by hand. You can't keep track of all the possibilities. So, you use technology to do it. It's totally rad. It's kind of the future of where this course, I think, is heading. If you guys come back and visit me in 10 years, when I've got even more gray hair, I got a feeling we're going to be doing this class a lot differently. You've already seen a lot of technological kind of insertions into the class. You're going to see another one today with these binomial distributions we're talking about. But you're going to see, it's amazing how much is done via computing power these days versus rote equations. I've been very, very careful about hiding equations from you guys, intentionally. I don't want you to memorize them because A, they're a dying breed, and B, unless you're in the theoretical realm of statistics, they're not important for you. I don't think anybody here is going to be a theoretical statistician. If you are, let's sit down sometime, have some coffee, and crunch some equations. But, I mean, for most of us, it's not that important. It's more important to understand what these numbers mean. What is a standard deviation? Does it matter if it's plus or minus? Not at all. It's a deviation from average. It goes up and down. So, that's it on that. Right now, I'm chicken flocks. So, let's get back into these. So, refresh my memory. We're not going to go too much further into this today. I'm definitely not going to give you homework today because that's insane. We're going to just, I want to finish the chicken example and share some technology with you. Okay? Let me put this down. We built 2 flocks yesterday, if I remember correctly. We built the Bertha flock and the Bertha Nancy flock. I'd like to get those numbers back up on the board and slam that shirt while we're at it. So flock number 1 consisted of 1 bird, just Bertha, just Bertha, and we made a distribution for Bertha. Okay, X is number of girls. Why are we doing this? Out of curiosity, why are we creating these distributions? Why is this a probability and not a certainty?
Because roosters don't lay eggs.
Good, but I'm buying chickens. But I'm buying chickens. I'm not buying roosters.
That's my point.
Boom, good. That's what I wanted to hear. I wanted to hear it's not a 100% chance if you buy a girl that it's actually a girl. Good, roosters don't lay eggs. But that's my question is, I'm not buying roosters. But I could be buying roosters, yes? There's a 90% chance that a pullet is actually a girl, which means there's a 1 in 10 chance it's a boy. So that's what I want to try to analyze the probability of that event happening. Good. So if I buy 1 bird, how many girls could I have in that little box?
0.
Or 1. And there's a possibility. I could either have none or 1. That little bird in that box is either going to be a girl or a boy. What's the chance it's a boy? Which means 0, here. Boy? That's 10%, yeah. 0. You have to kind of look at it like mathematically and Englishly. 0 girls means it's a boy. 1 girl means it's a girl. So you got 90% there. Sums to 100%. We're happy. Very, very happy. And the average number of girls per box or per flock of 1. Oh, careful. If it was a flip of a coin, a fair coin, yes.
Oh, yeah.
What's the average number of girls? 0.9. Exactly. You get 9/10 of a girl every time you buy a chicken. You get 9/10 of a girl. You get 9/10 of a girl. Good. Thank you, Megan, for that. There's a 90% chance that the chick in this box is a girl. You hear Megan say that again nice and loud. It's very important. Please, please.
I said, because you said it's a 90%.
I get 9/10 of a girl.
9/10 of a
And
girl.
you asked...
Why isn't it 90% chance?
That's a fantastic... Both statements you just made are correct. But realize that you're pointing at 2 different places on that chart when you say so. Thank you. This is a very, very good statement.
How can you be 9/10 of a girl? Like, I'm 100%
On average.
girl,
On
not
average. But you and Harrison are 50% girl on average.
I disagree.
It's all good. You see what I'm saying? I'm talking about an average, not a single person or a single person. Good? No, but Megan, what you said before that is uber important. Is uber important. Hang on. What you said was there's a 90% chance of a girl. That's this 0.9 right here, which is 90%. This 0.9 is the number of chickens that are girls in a flock of 1. It's 9/10 of each bird is girl. Now that's stupid to think about. You can't think of 9/10 of a bird, but make it a fraction with a denominator that's a whole number. It's 9 out of 10. So in other words, out of 10 birds, you get 9 girls. 10 birds, 9 girls.
Can I talk to you for a minute?
You're talking to me
I
right
forgot to
now?
send my test down to the testing center.
Say that again?
You forgot to send my test down to the testing center. So
I
I've
did.
been waiting down there thinking...
I'm sorry, Leslie. I completely spaced that. I thought everybody was in 105 that needed that done. Can you take it up here? Is that possible or is that not? Not in here, but up like upstairs?
Yeah, that's
Would that be
fine.
doable?
Yeah.
Apologies, sister. I thought everybody in 105. You know where my office is?
No, I don't know.
226. You can just sit in there and take it.
Okay.
Sorry about that. Okay. So, there's a difference between 0.9, 9/10 of a girl, and a 90% chance over here. These are the probabilities. That's the average applied to the probabilities. Good. Thank you. We'll come back to that as we build bigger and bigger flocks. All right. So, we add now Nancy. We now add Nancy in. Now we got two birds in the flock. Flock number 2. Let's slide this over this way. Okay. Two birds. Now, Megan, I think this will be more clear in this example. It's kind of fictitious with a sample size of 1. When we start drawing 2 and more, there becomes a difference between the probabilities that's pretty obvious and the averages. It's just that that average happens to be below 1, so it looks percentage-ish. So now we're going to go with number of girls again. Probability X. How many girls can we have in this flock?
0, 1, 2.
Good! None of them, one of them, or 2 of them. And this is where things started getting interesting. Because number 1, we had to start using that project number 2 math a little bit, yes? We had to start using that project number 2 math where we had to start multiplying probabilities. Because we assumed, what did we assume when Max goes in there and grabs these chicks and pulls them out and puts them in the box and goes back in again?
Replacement.
Good! We were assuming the numbers were with replacement, remember? That was something we kind of agreed upon. We said it's with replacement. Why? Because it's not. He's not putting them back, but why was it okay to assume it was? Do you remember? Jamie, go my friend. So small, and the population size is so big. You're saying the right thing, sister. So he's only drawing 4 birds out of hundreds and hundreds and hundreds of birds. We actually crunched the numbers, if I remember correctly. And even by taking 1 out of 700, you're only losing far less than 1%. 0.1% at most. Now, if he starts drawing a flock of 100 out of 700, that's no longer valid. But as long as your sample's pretty small, and your population's pretty big, did we define what that was? Pretty small, pretty big? Like how many you should draw before you start concerning yourself with? We didn't talk about that.
No.
A good kind of guideline, as long as you're drawing less than 5% of your overall population, you're pretty much safe. That's a pretty decent guideline to work off of. So for every 700, 1% would be 7, 5 would be 35. So if you're drawing a flock of less than 35 from those 700, you're pretty safe. You're not changing the numbers too badly. Anything above that, I'll have you guys analyze that in your last take-home exam. But that's kind of a rough guideline. This is why Gallup, when Gallup does polls, they'll randomly select 3,000 Americans and ask them about their opinions on Congress. Surprise, they don't like them. Okay, but they ask 3,000. The math they do on those numbers assumes with replacement, even though they almost always inevitably ask 3,000 different Americans. But they're drawing them without replacement. Well, 3,000 Americans of voting age, even with voting age, is a tiny percentage of those of voting age that are in the country. So you're nowhere near the 5% mark at that point. Is that fairish? Okay, so just keep that in the back of your mind for now. Okay. What were somebody's chances? Any one of them. Doesn't matter to me which one you like. 0. What's the chance of no girls, Andrew? 1%. And how did we get that 1%? Do you remember?
0.1 squared.
Awesome, Natalie Carter. 0.1 squared, because this is the unlucky where Max goes in, grabs a bird, and that bird is a boy. Puts it in a box. That only happens 10% of the time. Then he goes in again and grabs another boy, which also only happens 10% of the time. So it's 10% of 10% of the time. Now, you might remember this from previous math classes, means to multiply. But another way of viewing it is view it from the language of our projects. It's actually an and. He grabs the first one is a boy, and the second one's a boy. That's why it's multiplied. Natalie, hold the or. There is an or in this chart, just not there. There's no or. If he has to get 2 boys, he has to get, that one is a boy and that one's a boy. Just like down here. I want him to get 2 girls. Get the first one to be a girl, which happens 90% of the time. And then get the second one to be a boy, which also happens 90% of the time. Which ends up being 81% of the time you get 2 girls. When you buy 2 birds. Notice it's harder to get all girls when you buy more chicks. When you buy 1 chick, 90% of the time you get all girls. When you buy two, 81% of the time you get all girls.
You need to buy one, the lead, come back, buy one.
That, now we're just talking about math. You'll see that in a minute. That reminds me, never mind. Terrible math joke I'm not going to share with you. Now, we know this is 1%, very rare. This is an outlier. If you bought two roosters at the store, you'd go home and be like, what the hell? What happened? Why did we get two roosters? Well, you either got unlucky or that shipment was more roosters than it should have been, which is probably more likely to explain it. So what do we know this one has to be, percentage-wise? We figured out it had to be 18. JC, how come? Because, right, because you got 1 and 81, that's 82%. Whatever's left has to be 18% likely. But then in class, we started trying to figure out numerically, using multiplication, why it was 18, and we got stymied for a second, didn't we? Because we did 0.9 times 0.1, and that's 9%, not 18, right? But then what was the very last thing we kind of put together at the end? What were we forgetting? Say that again, Hattie.
There's two ways in which...
There's two ways. So Natalie, this is where your or comes in. So let's use the pictures to help us. Actually, let's forget the math for a second. I want one of these ladies to be a lady and one to be a rooster. Bertha, Nancy, describe it to me.
Either Bertha's a boy.
Bertha could be a boy and Nancy's the girl.
Or Bertha's a girl.
Or Bertha's the girl and Nancy's the boy. Now listen to what Kate just said. She used the word and twice and the word or once. Adding and multiplying. Here it is, ready? Bertha's a girl and Nancy's a boy. Natalie? Or Bertha's the boy and Nancy's the girl. Boom. That's where your 18% comes from. That's where your 18% comes from. Solid. Solid. Is that cool? I know, thrilling, Jenny. It's thrilling. Cool? Now we get ourselves a distribution. What was the average? How many girls we get on average? 1.8. And this is why I jokingly said, Kate, I know you were jokingly saying to me, go out and come back and buy one, go out and come back and buy one. On average, it's not going to matter. Because you're averaging 1.8 girls, you're averaging 1.8 girls per 2 birds, which is the same average as averaging 0.9 girls per 1 bird. It ends up being the same ratio, same slope, if you will. So every time you add a bird, you're adding 0.9 of a girl into your flock.
They're all equally girls.
Exactly. They're 90% equally girls. Exactly. Cool? Let's make it more interesting. Let's add Marge. Flock number 3. Can I come stand? Can I stare between you guys? Is that okay if I do that? No. So now we're... No? Okay, I'm going to stand behind you then. See how it is, Michael. Let's see how it is. It's all right. So there's our flock. We got Bertha, we got Marge, we got Nancy. Slide over here. All right. So, flock number 3. That's a fluke. Do it. Flock. 3 birds. Okay. Start the distribution.
0.
Good. Thank you. Number of girls. You guys become very, very big fans of the left column, yes? Because we know what the left column has to have in it, yes? 0, 1, 2, or 3. That's what you can have. Those are the random variables. Why are they called random? Yes, high fives. Why are they called random variables again?
Because you don't know what you're going to be.
Good. You don't know which one you're going to get, but
One of them.
you know you're going to get one of those. Perfect. And it's still discrete, yes? It's still discrete. That box contains either 0 or 1 or 2 or 3 girls. Can't have 2.5 girls in the box. You can have 2.5 girls on average. Maybe, mathematically, but you can't have 2.5 girls in the box. Unless the cat gets to them first. Okay? Alright. Sorry. So, who wants to grab a probability and give it to me? Grab anyone you want. Grab anyone you want. Figure it out.
0.001.
Jenny, for which one?
0.
Perfect. So, no girls. That's all roosters. That means Max had to have gone into the bin and grabbed a rooster, then gone exactly 3 times. Rooster 10% of the time, rooster 10% of the time, rooster 10% of the time. So just a bad roll of 3 dice there. And that ends up being a 1 in 1,000 chance. That should not have happened. That should not happen. If it does happen, what do you start suspecting about the guy's claim at the front desk? You start claiming that 90%'s off. If you start getting 3 roosters in a box, you're like, I mean, it can happen, but it just shouldn't happen, right? it shouldn't happen based off that 90% assumption. That's a little 244-ish for you thinking about right there. If something does happen that shouldn't have happened, chances are what you're thinking should have happened is the wrong thing to think. Whew, that was sideways as hell. Apologies. Grab another one for me. All three? Yes, all three's probably the nicest one, yes? And what's that one going to be?
0.729.
Good! Because he's going to go in and get a girl. Grab another to the third power, exactly. Thank you, Harrison. 0.729, is that what I heard?
Yeah.
Beautiful. Beautiful. So now we know that 73% of the time, we're either going to get all girls or all boys, which means the other, 27% of the time, we're going to fall into one of these categories. So it's getting more likely to get a rooster, isn't it? It's getting more likely to get a rooster because we're buying more and more birds. Every time you buy a bird, you're rolling a die with 10 sides, 9 of which have a little G on it, and 1 of which has a little B on it. So you're getting more likely to roll one of those B's each time. Okay, now, how do we deal with these? How do we deal with these?
Let you do 'em.
We don't?
No, we let you do 'em.
No! You learned nothing in 7 weeks, I make you turn it back around on you.
Could you return a chicken?
Nope, we didn't say anything.
Like if you got one of the chickens, like 90% chance it's supposed to be a girl, and like you can't figure out it's down there, could you like bring it back to the store?
Has anyone tried to do that?
This
How many of you
is
guys
a
keep
boy.
chickens? Who keeps chickens? No, it's just me. I
That'd
don't
be
know.
hilarious.
I'll take another one. This one didn't do it for me. Well, you have to wait like a year though.
Exactly.
And they wouldn't take back a full-grown bird, I'm assuming.
Well,
That's why Craigslist is full of roosters.
Be like
Roosters for free.
I didn't
No,
damage
I'm
it.
sure
Like,
she-
Everyone's roosters.
Pet stores have really weird policies. My friend was feeding his snake, and it wouldn't eat.
With a chicken?
No, with the mouse.
Oh, the mouse?
Yeah, and it would eat the mouse, and
Yes.
they just took it back. Petco, and they took the mouse back.
that's weird.
But-
Yeah.
That's a little nice.
Isn't that
That poor
weird?
mouse is like, I made it.
And they totally, we told them exactly what, hey, we tried feeding.
But I
them.
mean, when you buy these things, they're literally a day old.
Yeah.
And you're not going to know they're a rooster until
They
months
probably have
later.
like a 30-day.
They may have a soup pot in the back just waiting for stuff like that. Here's your rooster. Thank you.
Like, how fun would that be just to go?
Sorry,
and
I'm
just
not saying
grab
anybody.
chicken?
I'm saying I would do it that way. I'm saying it's not even have to do it.
What else are you supposed to do with
Stop! You're derailing the conversation. What is the chance of one of these things? Can we attack it like we did over there? Well, let's do it verbally first. Let's do it verbally. Back to the front. Great Metallica song. So to describe for me, let's do the one case. One girl. So now in that flock there's one girl. Describe for me all the ways that could happen. Their names are Bertha, Marge, and Nancy. So JC, go for it.
Can I just explain the math?
Sure, go ahead. Explain the math.
Okay. So like the P of X up there, there's one chance this way to 0 to 9.
Yeah.
Just like add one more to it.
Oh, good. So JC's looking back at the flock number 2, where we're multiplying 2 numbers together, and she said, I multiply 3 numbers together, 1 for each bird.
Yeah.
Let me ask a question. In that middle one, there were 2 things added together.
There'd be 2.
Thank you, Heather. There'd be 3 things added. There'd be 2 plus signs, 3 things added together, yes? Good. Why would there be 3 things added together? There's 3 different birds, any one of which could be the girl. That I want one girl. I'm doing the one girl case here, yes? So now I'm going to fuse everything that you guys just said into one thing. So JC's saying, okay, I add one more factor. So let's make in the first case Bertha be the girl. Bertha's the girl, so I'm going to put a 0.9 for Bertha. But if Bertha's the girl, what are Marge and Nancy? They gotta be boys, right? So that's 0.9 times 0.1 squared. But we're not done with that, are we? Because that assumes Bertha's the girl. But that's not the only way to get one girl. Who else could be the girl? Nancy! Both 2 votes for Nancy. Let's make Nancy be the girl. That means Bertha and Marge are both boys. And Nancy's the girl. Come around, you guys now. That's a 9. Sorry, that's a leaning far 9. Here we go. Are we done yet? I don't think we can be. Because we've assumed that Bertha was the girl. We've assumed that Nancy was the girl. Who else could be a girl? Marge, the other one. Marge, the one in the middle. So we can also have a boy on either end and a girl in the middle. Now this is kind of stupid the way I wrote all that out, yeah?
Yeah.
Yeah, it is. Because all 3 of those things that I wrote are equal to the same thing. They're all 0.009, yes?
Yeah.
I've written them that way because I want you to see the fact that you can actually identify what JC said and also verbally what you guys said in numbers. would it be easier, I think you're going to say yes to this, if I write this instead? 3 times, thank you, 0.09 times 0.1 squared. Can I do that instead? So you can if you want to, you don't have to. It's all multiplication, so you're safe. Harrison asked a great question about parentheses. It's okay to just have it up front like that. So basically, what you can look at is that right there is the chance of any one of the birds being a girl and 2 being a boy. And then 3 is the number of ways that can happen. Is that fair? It's easier than having to write it all out, like we did over here. I'm not saying that writing it out is a bad thing. I think it's a great thing. But mathematically, as JC pointed out, it's probably easier to go straight to the chase and get that done. Could we have done it up there in the 2 flock case? I'm going to slide back up here for a second. Could the 2 flock case have benefited from that as well?
2 times.
Thank you, Natalie Carter, yes? It's really just this. 2 times that, which ends up being the same thing numerically. 0.18. Thank you. Perfect. Fair enough? Is that decent? So are you seeing a pattern in those coefficients, yes? When the flock has 2 birds, that number was a 2. When the flock has 3 birds, that number came out being a 3. Let's see if the pattern continues, shall we? See if the pattern continues. Okay, let's do it. Yes, thank you. Now, can we try to go straight to that coefficiented number as opposed to doing the whole thing out?
Yeah.
Okay, so let's reason through it. I want 2 girls. 2 girls. If I have 2 girls, that means I also have to have,
One boy.
gotta have a boy too. So numerically, I'm going to have a 0.9 squared, thank you, and also a 0.1.
So you just move the square from the 1 to the 9.
Because I want 2 girls instead of 2 boys, exactly. What Jenny has just noticed, thank you, is that the coefficient, the exponents always add up to the size of the flock. Cubed, 2 plus 1, cubed, 1 plus 2, cubed, cubed, cubed. Back there, squared, squared, squared. Previous one, first, first. And that makes perfect sense. Every one of those parentheses indicates the probability of one bird's gender. That's what you brought up earlier, Megan. 0.9 and 0.1. Every time you, JC, add one of those factors on, like you said, well, perfectly, you're adding in one more factor, which makes the exponent bump up by 1. So your exponents always have to add up. Sometimes you don't see them because they're the first power, but these are all first powers right there, yes? So now my question is, what coefficient goes there? I hear a vote for 3. I hear a second for 3. All in favor of 3? Convince me it's 3. Aye, good. Convince me it's 3. I want some discussion. Kate, convince me.
You can either have bird A and bird B being girls, bird A and bird C being girls, or bird B and bird C being
They have
girls.
names.
I can't remember.
That's okay. That's totally fine. She's 100% correct. When you look at...
I'm just going to call it KFC.
That's totally...
Okay.
So that's exactly right. There are 3 different ways. There are 3 different ways of picking the 2 girls. Or conversely, 3 different ways of picking the 1 boy. You can look at it that way too. Same exact thing. So what does this end up being numerically? That's point, is that? Thank you, 243. Hey, it's our math class. 243. It's convenient. Which means that guy over there is going to be 0.027, is that right?
Yeah.
Okay, 027. I gotta listen on the screen. Say that again?
You do add up to 1.
And they add up to 1 because, hey, why do they add up to 1?
They have to.
Because they have to.
Okay, answer. Better answer?
Because you're gonna get one of those every time.
Yes, we have allotted for every possible arrangement of this flock. There are 2 possible arrangements of a 1-bird flock. 1 boy or 1 girl. There are 4 possible arrangements of a 2-bird flock. 2 boys, 2 girls, girl, boy, boy, girl. There are 8 possible arrangements of a 3-bird flock. All boys, all girls. Girl, girl, boy, girl, boy, girl, boy, girl, girl. Girl, girl, boy, boy, girl, the other 2 that I forgot. Well, I don't remember anything. They're all here. That's the beauty. You don't have to remember it. That's the best part. I screwed it up right there at the end, didn't I? But you don't have to remember it. I know there's going to be 8 outcomes because these coefficients add up to 8. There's 1 here, 3 here, 3 here, and 1 here. That adds up to 8. There's 1 there, 2 there, and 1 there. That adds up to 4. There's 1 and 1 there. I'm going to have a quiz for you guys in a couple weeks. It's called Pascal's Triangle. There's a beautiful, beautiful numerical thing going on right now called Pascal's Triangle that actually gives you these numbers for free. Now I'm going to give you one better by giving you a program at the end of the class today that does it all for you automatically. Because once you've seen it once, and we're almost done, Because now we got to build my flock with all 4 birds. It's cool, the pattern that arises. So let's slide over here. I'm going to go to the back of the room now. I remember lying to you guys years ago saying you wouldn't be on camera ever. All right. Here's my flock. I'm going to add Mary in, Mary the Delaware.
How come none of them are ready?
How come that can be what?
How come they're all girls?
He was hoping they were all girls.
How come they're all girls? Say that again.
They're all girl names. What if one of them's a boy? You're gonna
Wishful thinking. I wanted eggs and lots of them. I was hopeful. Positive energy. Come on, girls. Nothing wrong with boys, but I wanted eggs. And that's the whole point of this discussion. I don't know what I get. When Max brings the Happy Meal home, I have no idea what's inside.
One of these is not like the other.
Right? I mean, I know there's 4 birds, but I mean, who the hell knows what's inside? This last one's gonna answer that for us. Okay, so we got Mary, we got Nancy, we got Marge, and we got Bertha. Better question is, what's the next flock gonna be named? Oh, we didn't do the average. Thank you, ladies. Is the average 2.7? Doesn't it have to be? Now, 2 ways you can do the average. You guys run 1-bar stats to get the average. Did you run 1-bar stats? Boom. There's 2 ways you can get the average for this bad boy. There's 2 ways you can get the average for this bad boy. You can look at the pattern of the averages of the flocks. For 1 bird, the average is 9/10 of a girl. 2 birds, 1.8 girls per 2. 3 birds would have to continue the pattern. Every time you add a bird, you're adding 9/10 of a girl and 1/10 boy. So 2.7 would be your new average. Now, you could also run 1-bar stats, which is exactly what we've been doing for 7 weeks. Nothing wrong with either way. The only downside of 1-bar stats is you have to actually have the distribution in L1 and L2, yes? Don't worry. In about 15 minutes, I'm going to give you a program that automatically puts the distributions into your calculator for you. And that we don't have to worry about. Actually, this is the last one you'll have to manually enter in. We'll automate it from now on. I think you're getting the point of what we're seeing here. You're starting to see these kinds of experiments where there's a coin flip at work. And there is definitely a coin flip at work here. And here's the last coin flip. What happens when Sean buys his flock? All right, so let's go over here. Flock number 4. I'll put average for this one here. 2.7 girls per 3 birds. And all these averages, they average all to 0.9 girls per bird. So all you're doing is you're adding 1 more. So you know what the hell? Let's make flock number 4. 4 birds. Say that again.
Nothing.
Let's go straight to the average, because we know what it's going to be. 3.6 girls per bird, per 4 birds. Yeah. Your average number of girls is going to be 3.6 girls per 4 birds. Because every time you add another bird, you're adding 9/10 of a girl. Okay, so you can use this as good information. How many birds do you have to average 10 or 12 or 13 girls? Reverse to mathematics to figure that out. What you're essentially doing is you're taking how big the flock is times the chance of a girl, and that tells you how many girls you're going to get on average. Jenny, you figured that out. Excellent. Now, suppose we actually need to answer the question, or give the guy at the desk the answer to the question. When he told me you got a 90% chance of a girl, I said that means I got a 1/3 chance of a rooster in here. We haven't answered that question yet, how I figured that out so quickly, so let's figure that out right now. Number of girls. No, it's because it's binomial. If you understand the basics of binomial, which you guys are far beyond the basics right now, you could have answered what I did pretty quickly. And you'll see it here in a minute. Okay, so number of girls, chance. How many girls could I have had? None?
0, 1, 2, 3, 4.
2, 3, 4. Notice the pattern there too? There's always one more possibility than the size of the flock, because you have to include the 0 in there. Okay? Grab one and tell me what it is.
0.
0. JC, go. 0.1 to the power of 4. If you get home, you've got a box, and all 4 of those peeps in that box grow up to be roosters.
You take them back. You do man.
Well, you go back to the store and you go like, okay, look, I got 4 roosters. You told me it was 90% chance of a girl. The chance for roosters is 1 in 10,000. There's a problem with this. That shouldn't have happened, assuming that there's a 90% sexing rate going on. And maybe they do. I don't know what they do. Maybe they offer to sell them on Craigslist for you. I don't know. But this is how you say you present evidence, right? I'm not saying you're going to sue a feed store. But this is also how cancer cases are sometimes settled. When they look at cancer, a Civil Action. You ever seen that movie, the Ultra Volta movie from the late 90s, I think? He did the exact same thing. He saw a spike in cancer rates in a certain town in the northeastern part of the country. And all the towns around had nowhere near that spike, and he measured it, well, his statisticians measured it using something similar to this. And he was able to convince a jury that the spike was unusually high. There's natural fluctuations in things like cancer rates, but the one in this town was unusually high, and they were able to trace the cancer rates back to septic leaking from a factory, leaking into the groundwater, which happens all the time on the East Coast. It's happened for hundreds of years on the East Coast. So this is how you quantify these kinds of things. Why it's so important? You can actually quantify. You can't just say, you know, my aunt told me once. Unless your aunt is an actuary and actually crunched thousands of data points to get something like this, I don't really believe what your aunt says. No offense to your aunt. But if she can quantify it like this, I'm like, hell yeah. I got a little bigger. All right, let's do another one. 4. Absolutely, Heather. So this is 0.9 to the 4th, is it not? Mm-hmm. Which ends up being 6961? 6561. I'm not going to sit here and tell you that I did that in my head. I did not. But this is what I did when I asked that guy the question. So there's a 1/3 chance I got a rooster in that box. Because what I did was I did 0.9 times 0.9, which is 0.81. I dropped the 1 and called it 0.8. Then I did 0.8 times 0.8, which is 0.64. And then I added a few points back on because of the 1 I dropped. And that's about 0.66. That's about 2/3. Which means everything else up here has to be a third. And everything else up here has what in the box? At least a rooster, if not more than one rooster. That's where my 1/3 came from. It's not magic, just a little multiplication in my head. So I need to go right to that. I need to go right to that. This is like all the hard drives working. This is all the pumpkin seeds germinating. It's all the same problem. You seeing that? It's all the same problem. It's pumpkin seeds. It's the hard drives. Patrick.
Say that one more time.
About how is the pumpkin seeds?
No, the 1/3.
So this is essentially 2/3.
Right.
This number is essentially 2/3, 0.666666. So that means, since they have to sum to 100%, everything above it has to add up to essentially 1/3. Because 1/3 plus 2/3 has to equal 100% total. Is that believable, you guys? Believable? Good? Yes. So now the interesting thing is, what are the rest of them? Harrison, go. We're going to go to 3? Let's do 3.
Yeah, would that be 4 times 0.09 to the 3rd times
Write this down. Stay with you here. 0.9
to the 3rd times 0.1?
to the first, or just what? Now, I like the exponents. I see a 1 and a 3 that makes it a 4. Does he have the exponent on the correct numbers, 0.9 and 0.1? Is that correct? Yes? Yes? Do we like this 4? Why do we like that 4? 4 different combinations of assigning either, and there's 2 ways you can think about this, assigning the 3 girls or the 1 boy. So in other words, the boy could either be Bertha or Nancy or Mary or March. Or you can count the way the girls can be girls too, that also works. That's totally fine. I love it, Harrison, I love it. What does it end up being? 0.729.072, it's like 28% or something?
29.16.
Thank you. 29.16. Good, thank you.
This is a stat.
Oh, no, I cheated. I'm a cheating bastard. Look, I know that 0.9 cubed is 0.729 from the previous one.
Oh, okay.
Times 0.1 makes it 0.0729. I dropped the 29, make it 0.07, multiply it by 4, it's 28%.
Just follow up.
Cheating bastard. Cheating bastard. Oh, okay, another one?
So 2.
How about 2?
Yeah.
Okay, so let's do it, JC.
So there's gonna have to be.
Oh, let's do the numbers first. Let's do the probabilities first. So point.
So 0, 9.
Uh-huh.
2,
Good.
and then the 0, 1, 2, 3.
Good, beautiful.
Then would you add?
Oh, good, good. I'll tell you what, let's do this first. Let's do this for 1 as well, since we're already in this column, kind of. So it would be 0.91, 0.1 cubed here, correct?
Yeah, 'cause it's, yeah.
Right, and you're seeing a pattern again. The 0.1s are going down by 1 each time. It's 0 power down here. And the 0.9s are coming up by 1 each time. And that should make sense. You're increasing by the number of girls by 1 each time.
Yeah.
Now the only question is, what has to go here? Now continuing the pattern from before, remember I threw something out and Natalie goes, how do you know that? I'm like, it's not because I can count in my head, it's because I recognize a pattern. There were 2 outcomes for a flock of 1, 4 for a flock of 2, 8 for a flock of 3. Stands to reason there should be 16 for a flock of 4. Now I'm not going to try to do that out verbally, because it's very, very hard to actually verbalize all that. But pick one of these and tell me what the coefficient should be. Heather's going for this one, and she knows this one needs to be what? You know it. You know it. This means I have one girl in a flock of 4. It has to be 4, doesn't it? This has to be 4, just like this one has to be 4. Because this is, figure out how many ways we can get one girl. Well, either Bertha's going to be the girl, or Mary's going to be the girl, or Marge's going to be the girl, or, thank you, Nancy's going to be the girl, my children. So now the question is, what goes here? I heard a couple votes for 4. Natalie, what are you thinking over there? No, it's okay, she's thinking. Let's count them. Let's count. It's going to be just 2? Shall we count? Okay, here we go. No. Here we go, friends. These fingers represent the 2 girls. I don't have to count the boys, because if I pick the girls, the boys are determined, yes? Keep track with me. You count out loud. Here we go.
1, 2, 3, 4, 5, 6.
Already counted that one, right?
Yeah.
That's it. There's 6 ways. There's 6 ways. Check my math. Yes, didn't I? Because I'm magic? No, because I recognize patterns. Good. So this goes back to that. There should have been 16 possibilities altogether. There's 1 up here and 1 down here. There's 4 here and 4 here. That's 10 altogether. The last 6 have